got the liquid that is liquid. K1, K2 model, time is kind of new interesting quantum/classical model, and the reason we studied this model was motivated by experimentalists. So let me first start by acknowledging my collaborators. So this work, which I'm going to talk about, is mostly done with Ioannis Rufin-Hatzakis, who is now in University of Minnesota, and Craig Price, who is in Penn State, and some previous results were obtained with Yuri Suzuk, who is my PhD student, and with Peter Boyce, and I also acknowledge collaboration with FRG guys, Stefan Rasheri, Johanna Zollner, and Ronnie Tamari, who did the FRG study of this K1, K2 model. So here is the outline of my talk. So I will start with motivations, why we decided to study this model, and I will advocate also the importance of second neighbor key-type interaction to resolve at least most of the puzzles connected to sodium iridate. We heard a lot about this compound already. And then I will present and discuss this K1, K2 model. So K1 is key-type interaction on nearest neighbor, and K2 is key-type interaction on second neighbor. And then I will discuss both classical and quantum phase diagram. And I will show that this model actually has completely different quantum and thermal fluctuations. And basically, most of the results which I'm going to present today is in this preprint, and some finite temperature properties are in preparation, so we are going to submit it this way. Okay, so I don't think that I need to go to motivation, so once again, it was the work by George and Guignat, who showed that in this family of iridates, honeycomb iridates, it can be very large key-type interaction which come from this interplay between super exchange arising through this 90 degrees hopping. And what was also important that in this compound, Heisenberg interaction is there because 5d orbitals of iridium atoms are rather extended. And I think the main motivation for many experimentalists was that the spin liquid phase is in fact quite stable with respect to Heisenberg perturbation, and therefore it was, and maybe still, a big hope to see spin liquids in this compound. And basically in this original model, it was a part of spin liquid phase. It was two magnetic phases, simple two-supply ferromagnet, main state and small key-type interaction, and the splice phase. And when people start doing experiments, especially in the sodium iridate, then they found something else. I don't need to repeat many things what just said by Radu Koldea, but let me tell what were the questions for myself, what I could not understand in this compound. So first of all, from quantum chemistry results, it was shown that key-type interaction is indeed the dominating interaction. It's ferromagnetic one. So basically it fits to the description of this key-type Heisenberg model, and if you just take these values and plug it, you should get spin liquid, right? It's not in the spin liquid state. Both sodium iridate and lithium iridate, and now there is another compound, ruthenium chloride, they all order at rather low temperature. So this is question number one. Why sodium iridate orders? So second question is why Curie-Weiss temperature is large and antiferromagnetic if we see that the dominant interaction is ferromagnetic. So that was question number two. So basically the Curie-Weiss temperature which was obtained for sodium iridate was minus 135 Kelvin. So this we should understand too, I think. The third question was why it orders to zigzag phase, while in the original model this phase was not present. And basically in zigzag phase, you have two bonds, you have magnetic bonds, and you can have zigzags running in three different directions. And basically it was a suggestion first coming from Itamar and also from the paper of Rado's group that it should be further neighbor interaction to explain zigzag. Question number 4 actually comes from very recent work by biccamera group, and we heard about this yesterday. So it's basically that the order parameter, the spins, point in the phase diagonals. While if you do some order by disorder for nearest neighbor Kitaev-Heisenberg model, then you see that both quantum and thermal fluctuations choose cubic direction. And then if you add more terms, and we heard about this by Kingat yesterday, then in principle you can do some fine-tuning and get this phase diagonal direction. But we were thinking maybe there is something else behind this suggestion. So basically I want to point that the K2 interaction, the Kitaev interaction on the second neighbor basically helps to resolve all these 4 questions. So what we did with Yuri and with Peter, basically we took the tight-binding parameters provided by Roser-Valenti group, so it's Katerina Ferevtsova, Igor Mazin, and other people in this paper, and they provide the Hawking tight-binding parameters for both nearest neighbor and second neighbor. And what we saw that actually the second neighbor coming through a complicated path, so this path actually involves, so it goes from iridium to oxygen, then to sodium, and then to oxygen, and then to iridium. So it's a rather complicated path which connects second neighbors. Basically, if you do the strong coupling expansion and you derive your super exchange Hamiltonian for second neighbors, then you first of all see that there are 4 paths which all add up. They basically give you the same contribution, and then you get that in the second neighbor you have the same type of Kitaev interaction as for the first neighbor. So it's basically, it's kind of Z-bond here, so if you couple these iridium sites with these iridium sites, then you again couple YZ and ZX orbitals, like for the nearest neighbor for the oxygen, and yet then you get to the Kitaev interaction. So then what we did, we took some reasonable parameters which describe sodium radiate. It has some trigonal distortion, spin-orbit coupling 0.4 electron volt, Kunz coupling, Coulomb interaction, and then the Hawking parameters from this tight-binding model, and that's the number which we got for nearest neighbor and second neighbor exchange. So basically what we got is that the second neighbor Kitaev interaction is antiferromagnetic and is rather large. So basically in this minimal model we suggest for sodium iridate we need 4 parameters. Of course we can also have more parameters, but this seems to be the essential parameters. We also compute gamma terms for sodium iridate, and for sodium iridate it's rather small interaction, and these parameters give you zigzag ground state. And basically we also computed, I will not show it, the phase diagram for this model, and you can see that Kitaev interactions actually stabilize significantly zigzag phase. For this parameter we also compute Curie-Weiss temperature, and you can see that it's quite antiferromagnetic and very large. So in principle, if you play a little bit with these parameters, you can certainly get minus 125 degrees, so maybe taking instead of U2 1.8 electron volt, 2 electron volt. So basically you see the origin of this large antiferromagnetic Curie-Weiss temperature. So basically question number 1, why it is a question about zigzag is kind of answered. Question about Curie-Weiss also, we have some idea why it is a large antiferromagnetic. We also look to the locking of the spin direction to the special orientation, and once again it's related to the work presented by BGChem, and it's also easy to understand why the spins are pointing along phase diagonal. So if we consider this particular zigzag where ferromagnetic bonds are XY, then we can see that if we now look to the second neighbor K-type interactions, which are antiferromagnetic, then it's again X and Y bonds. And if you do fluctuation, so here we did basically Hubbard-Satonovich transformation, and look what is the spin fluctuational contribution into free energy. Basically, we immediately see that spin fluctuations select one of the diagonals in XY plane, and it helps to satisfy this second neighbor K-type interaction, isotopic K-type interaction. So basically here we didn't have any other fitting parameters. And if we vary our parameters but still stay in this zigzag phase, the direction will be still 45 degrees, quite robust. Okay, so I didn't answer only to one question, why it's ordered, and I will show you why it will order, why it is not spin liquid in the moment. But in any case, our suggestion was, okay, so since K-type interaction of the second neighbor is important, why don't we look to the minimal model and get rid of all Heisenberg interaction and basically consider only K-type interaction by analogy of J1, J2 model, which was studied by many people and apparently holds many interesting phases. So we were trying to see what is interesting about K1, K2 model. And once again, what is important in our microscopic calculation, we got it in a very symmetric way. So basically adding K2 terms does not lower the symmetry, because if we have two iridium sites, which from nearest neighbor connected by green and red bonds, so let's say by X and Y bond, then the second neighbor interaction will necessarily be Z type of interaction. That's why this model contains the same kind of C6 symmetry. Okay, so we start by analysis of classical K1, K2 model. And there's a usual way how one can do it is using the Lasinger-Tissot theorem. So basically here is, so we go to Fourier transform and we diagonalizing these lambda matrices. And what is important here, because it's not a Heisenberg interaction, now we have three types of eigenmodes corresponding to X type of spins, X directional spins, Y directional spin, and Z directional spin. And basically we have to look to the minimum of these eigenmodes, and one can immediately see that the minimum lines on the minimum sits on the lines in the K space, and basically what like these lines or that lines depends on the sign of K2 interaction, because it depends on this K2. So basically K2 interaction, which actually couples the triangle lattice, I will talk about triangle points separately, determine the type of classical degeneracy of this mode. So degeneracy of the ground state is free because it can be three different lines, and 2 to the power L, where L is the number of ladders, because the ladders are formed by non-zero K1 interaction. And basically this degeneracy, classical degeneracy, is not accidental because it's related to the symmetry of the Hamiltonian, and the symmetry is sliding symmetry. In a moment I will just explain what is this symmetry, and it's kind of gauge-like symmetry, and therefore for classical spin at t equals 0, this cannot be broken. Okay. So basically, let me construct, looking to this degeneracy, let me construct one of the states. Let me satisfy all the Z bonds. Basically, I will be looking to the minimum of lambda Z eigenmodes. So in this plot, so my Z bond, nearest neighbor Z bond, is my vertical bond, and my next nearest neighbor Z bond is my horizontal bond. So I consider both coupling ferromagnetic, K1 and K2, And basically I'm satisfying all these bonds. So I satisfy all the bonds on the nearest neighbor, and I satisfy all the bonds on the for the second neighbor. But because spins are classical, so the interaction